Section 5.4, the geometric and Poisson probability distributions. In many activities, the first to succeed wins everything. Use the geometric distribution to compute the probability that the nth trial is the first success. Use the Poisson distribution to compute the probability of the occurrence of events spread out over time or space. And use the Poisson distribution to approximate the binomial distribution when the number of trials is large and the probability of success is small. Hi class, how are you today? Oh, wait a minute. Did I start this late? This should have been the first thing. I'm just kidding. I put this one later on in the video because I wanted to show the focus points first, because there's a lot going on in this. I thought it'd just be easier to show you the focus points, and the focus points are your learning targets this time. So each of the focus points is something that we're really focusing on in this lesson. 3 different kinds of things: geometric probability distributions, Poisson distributions, and then using the Poisson to approximate binomial distributions. Let's get started. Geometric distribution. Geometric distribution is an experiment in which we repeat binomial trials until we get our first success, and then we stop. Let n be the number of the trial on which we get our first success. In this context, n is not a fixed number. In fact, n could be any of the numbers 1, 2, 3, and so on. What is the probability that our first success comes at the nth trial? So what's the probability that it comes at the first trial? Or what's the probability it comes at the second trial, or the third trial, or so on? So formula for the geometric probability distribution is probability of n is equal to p times 1 minus p to the n minus n. Remember, p being the probability of a success, and n being the number on which we get our first success. P must be the same for each trial, though. Using some mathematics involving infinite series, it can be shown that the population mean and standard deviation of the geometric distribution are mu equals 1 over p, and sigma equals square root of 1 minus p over p. So again, these aren't all that bad for mean and standard deviation formulas. An automobile assembly plant produces sheet metal door panels. Each panel moves on an assembly line. As the panel passes a robot, a mechanical arm will perform spot welding at different locations. Each location has a magnetic dot painted where the weld is to be made. The robot is programmed to locate the magnetic dot and perform the weld. However, experience shows that on each trial, the robot is only 85% successful at locating the dot. If it cannot locate the magnetic dot, it is programmed to try again. The robot will keep trying until it finds the dot and does the weld. Or the door panel passes out of the robot's reach. What is the probability that the robot's first success will be on attempts 1, 2, or 3? Since the robot will keep trying until it is successful, the geometric distribution is appropriate. So something's appropriate for the geometric if it keeps doing it until it's successful. You keep going until you get a success. In this case, success S means that the robot finds the correct location. The probability of success is 0.85. So for any n, it's p times 1 minus p to the n minus 1. Remember, just the 1 minus p is to the n minus 1, not the p as well. So it's 0.85 times 0.15 to the n minus 1. So when n is 1, it's 0.85 times 0.15 to the 0. For 2, it's 0.85 times 0.15 to the 1, and so on. And so we get these different probabilities. So probability of success on the first trial is just what p is, 0.85. And then probability of success on the second trial, 0.1275. Probability of on the third trial, 0.0191. The assembly line moves so fast that the robot has a maximum of only 3 chances before the door panel is out of reach. What is the probability that the robot will be successful before the door panel is out of reach? Since n equals 1, 2, or 3 is mutually exclusive, then probability that it's 1, 2, or 3 is the probability of 1 plus the probability of 2 plus the probability of 3. So we add up the 3 probabilities we have, and that will be 0.9966. This means that the weld should be correctly located about 99.7% of the time. What is the probability that the robot will not be able to locate the correct spot within 3 tries? If 10,000 panels are made, what is the expected number of defectives? Comment on the meaning of this answer in the context of forecasting failure and the limits of design. The probability that the robot will correctly locate the weld is 0.9966. Therefore, the probability that it will not do so after 3 unsuccessful tries is 0.0034. If we made 10,000 panels, would we expect, or forecast, 34 defectives, because we take 10,000 multiplied by the probability of defectives. So we would expect 34 defectives if we made 10,000 panels. We could reduce this by inspecting every door, but such a solution is most likely too costly. If a defective weld of this type is not considered too dangerous, we can accept an expected 34 failures out of 10,000 panels due to the limits of our production design. That is, the speed of the assembly line and the accuracy of the robot. If this is not acceptable, a new, perhaps more costly design is needed. So there's 2 things about that. First, you can use this to see, is the expected good enough for you? So is 34 failures out of 10,000 okay? Can you deal with that loss? If it's enough, move on. If it's not, get a new robot. Another thing you can do with this is a way to see if the robot is not as good as it expected. So if you do the 10,000 panels and you have more than 34 failures, if it's a lot more, something could be wrong with the robot, and you can test that. So that's how geometric probability distributions can be helpful. Poisson probability distribution. Poisson distribution is a binomial distribution where the number of trials n gets larger and larger while the probability of success p gets smaller and smaller. I'm going to pronounce this very wrong, but Simeon Denis Poisson? Yeah, I pronounced that wrong. Was a French mathematician who studied probabilities of rare events that occur infrequently in space, time, volume, and so forth. The Poisson distribution applies to accident rates, arrival times, defect rates, the occurrence of bacteria in the air, and many other areas of everyday life. As with the binomial distribution, we assume only 2 outcomes. A particular event occurs, a success, or does not occur, a failure, during the specified time period or space. The events need to be independent so that one success does not change the probability of another success during the specified interval. We are interested in computing the probability of R occurrences in the given time period, space, volume, or specified interval. So in this case, the Greek letter lambda is the mean number of successes over time. So we're using lambda now instead of mu. And R still is the number of successes in a corresponding time interval. And so lambda is just NP, just like it was with binomial. And sigma, the standard deviation, is the square root of the mean, so square root of lambda. Pyramid Lake is located in Nevada on the Paiute Indian Reservation. The lake is described as a lovely jewel in a beautiful desert setting. In addition to its natural beauty, the lake contains some of the world's largest cutthroat trout. 8 to 10 pound trout are not uncommon, and 12 to 15 pound trophies are taken each season. The Paiute Nation uses highly trained fish biologists to study and maintain this famous fishery. In one of its publications, the following information was given about the November catch for boat fishermen. Total fish per hour were 0.667. Again, this is their expected value. So it's not an exact amount, but this is how the average of the number of fish per hour. So it's not one, but it is about 2/3. Suppose you decide to fish Pyramid Lake for 7 hours during the month of November. Use the information provided by the fishery biologist in the Creel Chronicle to find a probability distribution for R, the number of fish of all sizes you catch in a period of 7 hours. For fish of all sizes, the mean success rate per hour is 0.667. So lambda is 0.667 for 1 hour. Since we want to study a 7-hour interval, we use a little arithmetic to adjust lambda to 7 hours. That is, we adjust lambda so it represents the average number of fish expected in a 7-hour period. So in 1 hour, it's 0.667. So we multiply the top and the bottom by 7 over 7, so 1 essentially, and we get 4.669 over 7 hours. For convenience, let us use the rounded value 4.7 for a 7-hour period. I assume the 0.667 was a rounded number anyway. So 4.7 is probably more exact. Since R is the number of successes fish caught in the corresponding 7-hour period, and lambda is 4.7 for this period, we use a graphing calculator to find the answer. On your graphing calculators, press the second button, then the distrib button, and then scroll way down until you get to Poisson PDF lambda R, and then press that button. What is the probability that in 7 hours you will get 0, 1, 2, or 3 fish of any size? So the solution you put into your calculator, and you should do this right now to test. Poisson PDF 4.70, because the mean is 4.7, and we're looking for 0 successes, no fish. So probability of that is 0.01. Find the probabilities for 1, 2, and 3 fish. Probabilities of getting 0, 1, 2, or 3 fish are about 1%, 4%, 10%, and 16% respectively. What is the probability that you will get 4 or more fish in the 7-hour fishing period? Well, what we did was we found out 0, 1, 2, or 3 fish. So we want 4 or more fish. So a couple different ways to do this. One is to take the probabilities we just found and add those up and then do 1 minus that. And that'll get it. Also, there's a button on your calculator called Poisson CDF, C standing for the complement, and put that into your calculator and you get 0.3096. There is about a 69% chance that you will catch 4 or more fish in a 7-hour period. So, because we did 1 minus 0.3096. Poisson approximation of the binomial probability distribution. In the preceding examples, we have seen how the Poisson distribution can be used over intervals of time, space, area, and so on. However, the Poisson distribution can also be used as a probability distribution for rare events. In the binomial distribution, if the number of trials n is large, while the probability p of success is quite small, we call the event a rare event. Put another way, it can be shown that for most practical purposes, the Poisson distribution will be a very good approximation to the binomial distribution, provided the number of trials n is larger than or equal to 100 and lambda is equal to np is less than 10. So n has to be larger than 100, but the mean has to be less than 10. As n gets larger and p gets smaller, the approximation becomes better and better. How to approximate binomial probabilities using Poisson probabilities. Suppose you have a binomial distribution with n is the number of trials, r is the number of successes, and p is the probability of success. So if n is greater than or equal to 100 and np is less than 10, again the mean, then R has a binomial distribution that is approximated by a Poisson distribution with the lambda being NP. So probability of that is this formula. So the probability of R successes is e to the negative lambda times lambda to the r over r factorial. Note that lambda is the expected value of the binomial distribution. Isabel Briggs Myers was a pioneer in the study of personality types. Today, the Myers-Briggs type indicator is used in many career counseling programs as well as in many industrial settings where people must work closely together as a team. The 16 personality types are discussed in detail in the book A Guide to the Development and Use of the Myers-Briggs Type Indicators by Myers and Macaulay. Each personality type has its own special contribution in any group activity. One of the more rare types is INFJ, introverted, intuitive, feeling, judgmental, which occurs in only about 2.1% of the population. Suppose a high school graduating class has 167 students, and suppose we call success the event that a student is of personality type INFJ. Let R be the number of successes, INFJ students, in the n equals 167 trials, the graduating class. If P equals 0.021, will the Poisson distribution be a good approximation to the binomial? Well, we just see if n is greater than 100. Yes, it is. And is NP less than 10? Yes, it is. So the Poisson distribution should be a good approximation to the binomial. Estimate the probability that this graduating class has 0, 1, 2, 3, or 4 people who have the INFJ personality type. So we look for the Poisson CDF, because we want to add up all of them from 0 up to 4. Lambda is 3.5, and we want up to 4 successes, so 0.7254. The probability that the graduating class will have 4 or fewer INFJ personality types is 0.73. Estimate the probability that this class has 5 or more personality types. It's just 1 minus that, so 0.2745. The probability is approximately 0.27 that there will be 5 or more INFJ personality types in the graduating class. So if we just want to find the complement, we just do 1 minus that. Alright, now time for the sponge. Since there were 3 different things going on in this lesson, I wanted to make sure that we covered all 3. in the sponge. I apologize for the size of the sponge, but I don't think it's actually that bad for the sponge. You just have to remember the different formulas. So, for number one, an artist is creating a logo for a company. In her contract, it states she is not allowed to leave until she creates the logo the way the company wants it. From experience, she believes that she will have a 90% chance of getting the logo right on one try. A, what is the probability that she will get it right on her first 5 tries? And B, it takes about an hour for each try, and she has an appointment in 4.5 hours. What is the probability that she finishes before her appointment? Number 2, while hunting, there is a 10% chance of finding a deer for each hour you hunt. I made up that percentage. Sorry, I don't hunt. I don't know the percentage of finding a deer when you hunt. To give yourself a good chance of finding enough deer to feed your family, you decide to hunt for 5 hours. I actually think that's probably not enough time to find enough, but okay, I'm going with it. A, what is the formula to find the probability of finding R deer? B, what is the probability of finding 0, 1, or 2 deer? And then C, what is the probability of finding at least 3 deer? And number 3, 2% of people in the world have blonde hair. You look at a randomly chosen group of 200 people. A, will the Poisson distribution be a good approximation of the binomial? Explain. B, what is the probability that there will be 0, 1, 2, or 3 blonde people in the group? And C, what is the probability that there will be at least 4 blonde people in the group? All right, that's it for the lesson. Once again, please make sure to take notes in the entire lesson. Don't forget to rate yourself back at the beginning, attempt the sponge, take a picture of everything, submit it all to Google Classroom, and have a good night.